A 19 ohm resistor and a 12 ohm resistor are connected in parallel with a 9 volt battery. A single ammeter is connected to measure the total current of the circuit. Well, this is technically 13A. It says 14A, but it's 13A. Using symbols found in the reference table, draw a diagram of this circuit. So the important thing here is that we have two resistors. They're connected in parallel. We have a battery, and we have an ammeter. That's all the relevant information. So first things first, we have to know what a resistor looks like. If you look at the reference table, they tell you that this is what a resistor looks like. And they also why did I write resistory? Resistor, that's what a resistor looks like. And a battery, they say, looks like this. Right, this is all from your reference table. I believe page 4, I might be wrong on that though. And you have an ammeter, which looks like that. And they're all connected in parallel, or at least the resistors are connected in parallel. So first things first, I always start with writing my battery, or drawing my battery. And now let's get our two resistors in there. Now if you see, let me redo that actually, it looks like a mess. Now if you look, you can see that I connected these in parallel. How do I know I connected them in parallel? Well, if we follow the current from the source, we reach this junction right here, this point right here. And at this point, the current can either go down and around, or it can go right and then around. So that implies that we have a choice. This current can either go here, or it can go here. And that's what the definition of a parallel circuit is, where that current is branching off into two possible directions. Right? Some of it will go to the right, and some of it will go down. But in the end, they'll all come back around, recombine at this point, and then come back around to our battery right there. So that's how I know this is a parallel circuit. So you have to draw it this way. If you drew it this way, right, where there's a resistor here, and like a resistor here, and a battery here, that wouldn't really be parallel. In fact, that wouldn't be parallel at all. That would be a series circuit. There's only one possible route for that current to take. There's no point where that current can go any other direction. So that would be series, but this right here is a parallel circuit. Now if you look, there's something we forgot to do. We forgot to do the ammeter. Well, I didn't forget, I was just holding off on it. So the ammeter always has to be connected in series with your circuit. So you could put it here. Right? Put it in series with your battery. Put the little ammeter right there. Why do we put it there? Well, let's say we put it right here. Let's say we put our ammeter right there. And let's imagine our current going around. Let's say we have, I don't know, 10 amps coming out of that battery. Well, if we put the ammeter here, it's going to read that true value of 10 amps. If we put it over here, what's going to happen is that current is going to get to this point. Let's say 4 amps go down here and 6 amps go to the right, and then it comes around. And now we would get a reading on this ammeter of 6 amps. So we wouldn't get a proper reading. The other place we could put it, we could put the ammeter after they recombine at this point. So we could put the ammeter right here. That works as well. But we can't put it there, we can't put it here, we can't put it here or here or here. We can't put it anywhere after that current is broken up. We could put it before it's broken up or after it recombines. But we can't put it anywhere where that current is split in two. Or more. You could have circuits with more than just 2 resistors or 2 paths. Right? We can have infinite number of paths for that current to take. But the ammeter, I think, is just nicest looking right there. So that's your diagram for this circuit. Next thing they wanted us to do, they want us to find the equivalent resistance in this circuit. So they wanted us to find Req. If you look at the reference table, there's 2 separate formulas for finding the equivalent resistance. There's Req equals R1 plus R2 and so on, and then 1 over Req equals 1 over R1 plus 1 over R2. Now, why do we have two of them? Well, one of them, this one right here, is only for when you're dealing with series circuits, where you only have that one pathway for the current to take. This one right here is for when you're dealing with parallel circuits. So clearly we have a parallel circuit, so let's go ahead and use that formula. So what we do is we plug in our values. We have a 12 ohm resistor, they told us. So plug in 12 ohms for the value of R1. And we have a 19 ohm resistor. Am I getting that correct? 19 ohm, 12 ohm, yes. So let's go ahead, plug in that 19 ohms. And all of that is equal to 1 over the equivalent resistance. So let's find out what 1 over 12 plus 1 over 19 is. Now the way I like to do this, I like to make it into a decimal first. So 1 over 12 is a decimal, gives me 0.083, plus 1 over 19 as a decimal, gives me 0.053. Let's combine those two. 0.083 plus 0.083 plus 0.053. I get 0.156, or 36, excuse me. 0.136 ohms equals 1 over the equivalent resistance. Now, I don't care about the value of 1 over REQ. What I care about is REQ. What I care about is the equivalent resistance. So what I have to do, take this and flip it upside down. Now, the way you flip things upside down, the way you flip fractions upside down, you take the reciprocal, is you raise it to the negative first power. You take that to the negative first power, you get REQ, that flips upside down, and take this, you plug into your calculator, that to the negative first power, you should get 7.35 ohms for your equivalent resistance.